So what if the function you give to map isn't constant time? Well, then what you get is the sum of the work for x0, f on x0 plus the work for f on x1 plus dot 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 the work for f on x n minus 1. Okay, so if you map a non-constant time function, then what you get when you do that with sequences is the same thing you get for lists, the same thing you get for trees, which is that the work is overall the sum of doing the time for doing f to the first element, doing f to the next element, doing f to the xn minus 1. What about the span? Well, in general, if you think about doing the span, then the idea is that when you're doing a map on sequences, then what it's going to do is it's going to do f on x0 in parallel with f on x1 in parallel with f on all the way up through xn minus 1. And so if you're doing all of those in parallel with no overhead, then you just wait for the longest of them, right? So whatever the longest one takes, you get the time for that one. That is, you get the maximum of all of those. Okay, and that's the deal with map on sequences. So now, the last bit we'll talk about for right now is reduce on sequences. So just like what we talked about last time for lists, reduce is going to take a combiner function that takes two results and combines them into one, and it's going to take an element, and then it's going to take a sequence of elements and squish that down to a single element. So the behavior for this is that if I reduce some operation, let's call it, I don't know, let's call it, I don't know, sharp sign with a base case e, and I do that on my sequence x1 through xn, then in general what I get is x0 sharp x1 sharp x2 sharp x n minus 1. Or I get e if the sequence is empty. Okay, it's a little abstract, so let's do an example. If I reduce with the add things together combiner with 0 on that list, let's run here. Yep, sorry. If I reduce with the add things together combiner with 0 on 1, 2, 3, I get that. If I reduce with the multiply together combiner with 1 as the base case on that, then, okay, that wasn't the best example because those two turn out the same. Multiplying all those together gives me 24. Adding them together gives me 10. If I reduce with the combiner that says take the bigger of them with, you know, 0 is the base case, then the biggest of them is 4. Okay, so the point is that for reduce, I can put in a way to combine two things, and then I kind of pairwise combine things all together. So this statement of the behavior is a little ambiguous. Unless the operation that I give, which in the examples I just ran was plus or times or max or something, is what's called associative, which means that x sharp y sharp z equals x sharp y sharp z in the two ways that you might think of that as being associative. Okay, so one thing you can do is you can assume that the sharp that you're given, the operation that you're given for combining results, is associative. Another thing you can do to like what reduce actually does is it picks a certain balanced tree parenthesization. So when you do something like the reduce on that, then you're going to get something like 1 combined with 2 combined with 3 combined with 4. And not 1 combined with 2 combined with 3 combined with 4, or 1 combined with 2 combined with 3 combined with 4. Okay, it's going to pick a balanced decomposition, sort of like your tree reduce that you're doing, exactly like your tree reduce that you're doing for homework, assuming the tree is balanced. So reduce won't string things out into a line and just do what the list code would have done. It'll do something kind of tree-like. It doesn't actually matter exactly like what balanced tree it picks. I think in fact the implementation does something involving powers of 2, where it says does sort of successive powers of 2 and then does yeah, like does successive powers of 2 in order to kind of write the length of the list in binary and do things in parallel. But for our purposes, what you can do is you can just assume that it's sort of doing the straight balanced tree, and we'll always analyze reduce, assuming the input is actually a single power of 2. And so you can think of it as doing the balanced tree parenthesization, meaning like it does what your code from the homework does on when the list is balanced. Okay, so in terms of behavior, what it's doing is basically combining things together. And if, like usual, the operation that you give is actually associative, then it just, you can think of it as just like merging the things together by putting an operation between every two elements of the original input. Okay, so what can we say about the work of this? Well, let's assume that the operation we're doing is constant time. Plus is constant time, times is constant time, max is constant time, right? So a lot of these examples are constant time. Then reduce sharp with some base case on a sequence like this. Is going to be linear time. So just like if you had written it in a list or written it for a tree explicitly, it's going to be like that. And the span, similarly, is going to be log n, which is what your implementation of reduce for trees in the homework that you're working on now should really turn out to be, right? So like if you do a reduce with a constant time combiner like plus or times or max or string append or whatever, something like that, then you should get a log n span. Okay, which is to say that if sharp is not constant time, then it's a little bit hard to say like what the work in the span of reduce are in general and in the abstract. Instead, it's just to say like, think of it as the tree code from homework and use the tree method to extract and solve a recurrence for it. Is the best way to analyze the running time there if it's not constant time. So just pretend that seek.reduce of sharp and e, what you should pretend is that it's tree code where leaf of x, well, okay, actually, I shouldn't do this yet. We'll get back to this on Wednesday after the homework is due. Okay. Okay. Can't say that pretend exactly in full general yet without giving away the homework solution. Okay, but that's reduce. All right, so with all of this in mind, let's come back to the example that we did way back in the very beginning of the first class, right? That was sort of an example to set up what we're going to talk about this semester. Well, now we're totally finally back to the point where we can talk about that in some more detail. So the example, remember, was to count the number of people in the class who had taken Count to 11 last semester as opposed to taking it the semester before that or sometime earlier. And so we're going to represent the classroom as an int sequence, so a sequence of sequences where conceptually the sequence may be 1, 0, 1, 0, 1, 0, represents a classroom that has 3 rows with a yes, no, yes, no, yes, no. Okay, and then to like actually write this in the file, I can say something like, the example is seek.fromList of 1, 0, 1, seek.fromList of that and 0, 1, 0. Okay, and then now I've created my example classroom. And so the first thing we can do is we can write a function sum, which takes an s, which is an int sequence, and produces an int and adds up numbers, right? So when we did this example, like as a running example, the idea is like first we're going to count across each row, and then we're going to count down the column that results on the side. And so our count each row or column function, well, how to do that? Well, if I want to add things up and I want to do a sum, okay, this is a little bit of a homework spoiler. to add things up, I'm going to reduce with the add two numbers combiner, and 0 is the base case on S. And then if n x goes to x plus y, okay, so sum is there. So sum of seek dot from list of 1, 0, 1, if I count that row, I get 2. If I count the 0, 1, 0 row, I get 1. If I count 2 and 1, then I should get 3. Right, so like sum is adding things up. Okay, so now finally, if I'm going to count all of the students where the whole classroom is a int sequence producing an int, right, then the algorithm was we're going to first count each row in parallel. And so now we have nice terminology for that. That's seek.map of sum, because sum is the function that counts a single row. We map that. That's counting all of the rows in parallel. And then I want to add up the column that results. Well, that's another final sum. And so overall, if I count the example, then I get 3, right? Which is what I'm supposed to get, because the data there is supposed to represent 3 people taking Comp 211 last semester. Okay, so that's what's going on there. And so now if we want to analyze the work and span of count, then the way we want to think about it is this. There's 2 phases. Phase 1, which is the map, phase 2, which is the sum. And for each phase, we have an input, and we can think about the work and the span. All right, so now, suppose that the classroom is n by n, right? So for that to be true, like up here, I should have added another thing to the example so that it's a square. There. So for map, right, if I'm doing map of sum on students, the input to map is going to be of size n by n, right? Because map gets the whole students as input. So how do we figure out what the work is? Well, we have to think about phase 1a, which is the mapped function, which is in this case sum. And the input to the mapped sum is of size n, right? So like if I have an n by n classroom, then the sum that map tells you to do is getting applied to a single row. A single row has length n. So the mapped sum function is going to have order n work for each of those. and order 1 span for each of those. Sorry, the map sum is going to have order log n span for each of those. And that's because if you look at the definition of sum, what is sum? It's a reduce. What are the function inputs to reduce? It's plus and 0. Okay, so it's the case where reduce is doing a constant time function on a sequence. And what did we say up here? What we said was that in that case, reduce is taking linear time and log span. So it's the same as a tree reduce. Okay, now that we figured out what happens for each function that map does, how do we figure out the time for map itself? Well, we said that the time for map was the sum of the times for each of the functions. The whole classroom is n rows, each of which map the sum function. Each sum function was order n times of those is order n squared. What about the span? Well, what we said for map was, for the span, when you're doing a map, it's the maximum, the biggest of the times for all the functions you're mapping. All the functions you're mapping take log n span, so it's just log n span overall. Okay, so that's phase 1. Phase 2 is the sum. The input to the outer sum, right, this one, is again of length n because that's the output of the map. We're mapping the sum on a function, on a sequence with n rows, so we get n numbers in the final column down the side. And then, well, we know what sum does on that, which is log n. And then the key point is that we're going to add phase 1 and phase 2 to get a total. And the reason for that is when we think about the code, what the code does is first it does phase 1, right? First it does the map sum, and then it does the sum at the outside. Okay, and so if we add them, then, well, in this case, that's the same as taking the max, because adding order n squared and order n squared gives you order n squared, and adding order log n for the longest row and another log n for the column down the side still gives you order 2 log n, which is order log n. And so overall, doing the two phases together give you order n squared work and order log n span. So the work is exactly the same as what we said in the first lecture, right? So like in the first lecture, we said, well, I'm doing n squared pluses. Okay, that's order n squared time. The span is smaller than if we had done this for lists, because what we're doing is we're only charging, and smaller than if we'd done it for trees, because we're only charging for the span of essentially a single reduce. When we do the map, we don't get another log span coming from doing the map itself like you would if you did it for trees. Instead, we just get the log span for the reduce and then for the reduce at the end, which is to say the real parallelism in this example that we started off the course with is that in parallel you can add each row. When you're adding each row, you can do that on a tree and get a log span for that. And then you're left with a column at the end that you have to add up. And when you're adding up that final column at the end, that's again just a log span thing, because you can do that on a tree and get some binary parallelism going there. Okay, so overall we get order n squared work, order log n span, which gives us pretty good parallelizability, because you remember the parallelizability is the work divided by the span, which tells you approximately how many processors you can use. And in this case, n squared divided by log n grows pretty fast, which is good. That means that we can get a lot of parallelism on this example. Okay, so big picture, what we've seen is that we can write some client code, right? We can write an algorithm that processes some data. We can write, in this case, our goal was to add up the numbers in a square grid of numbers, right? We can write this. The point is that, in some sense, using higher order functions like map and reduce, we don't need to know whether we're working with trees or lists, etc. Right? When you look at this code, we could write this code here essentially the same for lists or for trees or for array-backed parallel sequences with n-way parallelism or anything you want. And the reason is that the higher order functions we're using, reduce and map, can be implemented for all those data structures. And so we don't really need to think about exactly how things are represented, because we're using these higher order functions to abstract the loops that we're running over the data. And it's the loops that we're running over the data where we were once upon a time expanding things out in terms of recursion and caring exactly about how things are implemented. So one lesson from today is that we can kind of get away from the actual representation. And the other is that we can give an abstract model of behavior and cost and think about things in terms of that abstract model, right? I don't need to tell you exactly what sequences are. Instead, I can say, well, you can do this length thing and this end thing and this map thing and this reduce thing, and then you write the rest of your code in terms of map and reduce, and you explain what the running time is for map and the running time is for reduce. And then if I tell you, well, this is the time that map takes and this is the time that reduce takes, then now for this code that's written as a composition of maps and reduces, you can think about the running time. Well, I know what the running time for map is, I know what the running time for reduce is, add them up, combine those two ingredients together, you get the overall running time. So we're using an abstract model of how long things take. Here's the work for a reduce, here's the work for a map, and then putting that together to analyze the running time for the code. So we don't need to be drilling down into the details of, is it a list, is it a tree? Here's how we wrote things out by recursion. Instead, we can start to toss around maps and reduces and get code that way. Okay, so in the homework for tomorrow, you're getting some kind of practice with doing that, but where you know that the data is still actually a tree, but in like all pairs and filter and flatten and things like that. You want to be writing the code just in terms of maps and reduces without actually knowing or caring exactly what. So like all your implementations of those should translate to sequences as well. And then in lab tomorrow, we'll get some practice with writing some sequence code directly. Okay,